Okay. I'm going to talk about the transonic shocks in steady two space-dimensional compressible Euler flows. Okay. Here is a picture of transonic shocks in a supersonic nozzle. The gas flows from left to the right. So here is a supersonic flow that contains many discontinuities. Then by passing this normal shock, it becomes a subsonic flow. So here is a transonic shock. Okay. Transonic shocks has many applications in gas dynamics, including the supersonic units of turbojets. Yeah. Our aim is to study the transonic shocks by suitable mathematical models. Okay. Our mathematical model is a boundary value problem of the Euler system. Okay. First, we consider the domain. Our domain is a rectangle in the plane with length 2L and the height h. Okay. It represents a straight arc. Okay. This is a two-dimensional steady Euler system. Okay. The first one is the conservation of mass, and these two are the conservation of momentum, and the last one is conservation of energy. Okay. And here rho is the density, and p is the pressure, and uv is the velocity. And we consider here polytropic gas. So the pressure p and the entropy s and the density rho has this relation. Here K0, S, C nu, and gamma are constants. Okay. And E in the conservation of energy is given by this. And here C is the sonic speed. Okay. And we define the Mach number. For m larger than 1, it is supersonic flow, and for m less than 1, it is subsonic flow. Okay.
Or maybe slow down.
Okay. Here we consider the boundary conditions.
Can you
Okay.
maybe write down equation in our box?
Oh.
Is it okay?
I think Minjin has introduced this, so
No,
maybe you have got familiar with this. Okay.
maybe write down the equation.
Yeah.
Okay?
Write down the equation.
Yeah.
Okay. Because I have many things to talk later.
Oh, many
so-
things to talk.
yeah.
Yeah, maybe write down.
Okay. Okay, later we seldom use this. We later we use another form of this. Okay. Yeah. So here we consider boundary conditions. Okay. And we assume the upper and the lower boundary are the solid walls. So we propose the slip condition here. So v equals 0. And at the entry here at the entry we assume the flow is supersonic as shown in the picture. So the Euler system is hyperbolic for supersonic flow. So here we need to propose all of the state. Okay. So we give u0 means the velocity and the pressure and the entropy are all given here. Yeah. And at the exit, we assume the flow is subsonic. So one and only one boundary condition is necessary. Okay. For a physically interesting case, we give the back pressure here, means that we have a condition of pressure here. Okay, given pressure. This is a physically interesting case. So now we have a boundary value problem, the steady Euler system, and the domain, and the boundary conditions. Okay. And now we specify the structure of the solution, namely, what solution are we looking for? Okay. We specify the structure. Now, the first thing is that there's a shock front. Okay. The shock front is given by a function f, which is C1. Okay. For f is given, then the duct is separated too. Here is the supersonic domain, df minus, and here the subsonic domain. Okay. And we assume the supersonic flow and the subsonic flow are both C1. Okay. This is very important. Okay. And this satisfies the Euler system and the boundary conditions point-wise because we assume it is smooth. Okay. And on the shock front, there should hold the Rankine-Union conditions. Okay. Okay. This is the Rankine-Union conditions for the Euler system. Okay. Minjin has introduced how to derive it. Okay. Here the bracket means that the jump of a quantity across the shock front. Okay. The other condition is the entropy condition, which means that the pressure should increase by crossing the shock front. Okay. So from supersonic to subsonic, the entropy should increase. Okay. So if we get U minus, U plus, and F satisfy these conditions, we call this as a transonic shock solution. Okay. So now we have a boundary value problem and the space of function. So the space of solution so we have formulated our mathematical model. Okay. We know that special solutions play the fundamental roles in the studies of gas dynamics and systems of conservation laws. I may say that if we don't have a special solution, we can almost do nothing in multidimensional case. So special solutions are very, very important for us to study the multidimensional phenomena of gas dynamics. Cool. So for our problem, we have a very simple special solution. namely a piecewise uniform normal shock. Actually, Minjing has established this solution for the potential flow. It is the same, okay, which means that the supersonic flow, okay, it is a constant, and the subsonic flow also a constant, and the shock front is a straight line, okay. So we call this a background solution. Later we will study its stability. Then how to solve this special solution? Okay, it is very simple because the supersonic flow and the subsonic flow are both constant, so it satisfies the boundary conditions. Okay, also the OLI system, and we assume that the velocity terminal v is 0, so it satisfies the boundary conditions. So the only thing is to check the IH conditions and the entropy condition on the shock front. Now this is Rankine-Egonia conditions. Okay, here. Since the shock front is straight line, so f prime is 0. Okay, we assume v is 0, so the third one is trivial. So we only have the first, the second, and the fourth line. Okay. Okay. This is the IH conditions. Okay, so 3 equations, and we also have 3 unknowns, namely the pressure and the density and the velocity for the subsonic flow. Recall that for supersonic flow we know that because we have the Cauchy data, it should be given here. So for the ρb minus and pb minus and the ub minus is given. So we have 3 equations and 3 unknowns. Actually, we can uniquely solve the subsonic flow by the given supersonic data. So this can be uniquely solved. Yeah. So we construct a special solution here. This might be the simplest special solution in the studies of transonic shocks. Our aim is to, it would be very good to show that such a special solution is stable, to show that, the transonic shocks we can observe in the physics. But actually for this, we cannot show it is stable. It is unstable, okay? Which means that if we perturb the supersonic flow slightly, or the back pressure slightly, then there may not exist such special, there may not exist such transonic shocks. Such solutions, U minus, U plus, and F might not exist. Okay, so such solutions are actually not stable. Okay. Here, the function space we use are some weighted Hodder space, but we will not delve into these technical details. Okay. So the instability proved in these papers. Okay. Now there are some remarks. Okay. Up to now, there are only partial results for the 3D case because the 3D OLA is much more complex. Okay. The other thing is that we assume that the supersonic flow is smooth in our definition of a transonic shock solution. But we saw in the picture that the supersonic flow actually not smooth. But up to now, there is no any result if the supersonic flow is not smooth. No any result. Okay. If you're interested, I will explain later. Okay, if I will have time. The third one is about the existence of a smooth supersonic flow. Okay. Here we have the supersonic Cauchy data, and here we have the slip condition. Okay. So for the supersonic flow, we can just solve it because it is now okay for the supersonic flow. We have initial data and boundary data. So by the local existence of smooth solutions of initial boundary value problems of hyperbolic system, okay, if there hold some compatibility conditions at the corners, and if the perturbation is small, actually we can find the supersonic flow in the whole duct. Okay, if the perturbation is very small. Okay, so in the following, we always assume that the supersonic flow is given. So our aim is to find the transonic shock front and the subsonic flow, and it is actually a one-phase free boundary problem. Okay. The fourth remark is about the stabilization effects of transonic shocks in ducts. Okay. We just have shown that the special transonic shock is not stable, okay, not stable, which means that our model is too simple, too simplified, okay, even for OLA. Okay. So this model misses some stabilization effects. Okay. The first stabilization effect we studied is about geometry, which means that we consider flows, symmetric flows, or flows in divergent nozzles. Okay. So for example, okay, we consider flows in such nozzles. Okay. We can construct special solutions by considering the Euler equation in polar coordinates. Okay. This is the Euler equation in polar coordinates, and we construct special solutions by considering flows depending only on R. We assume the flow depending only on R, so we can construct special solutions, okay, involve transonic shocks. Yeah. This is the first one. Okay. and the stability was established in the paper, okay, this paper. And it is interesting that there appear some non-classical non-local problems. Okay, this is never seen before. We see here is a second-order elliptic equation, and here is a lower-order term. It is a free zero way. It is a boundary data. But on the boundary here, we have a Robin condition. So phi itself is unknown. So we have such a non-local term. A non-local term in the second-order equation. Okay. We derive this because we will see later that our Euler system is an elliptic and hyperbolic composite. The elliptic part and the hyperbolic part. The hyperbolic part has a transport effect, which may lead to such non-local elliptic problems. Cool. Okay. Another stabilization effect is the frictions. We should consider that the compressor Euler flow in the duct, there are frictions. Mathematically, it means that there is a damping term in the conservation of moment term. Okay. Here, mu is a positive constant given by sigma over h. H is a height of the duct, and the sigma is positive. It is a Darcy friction factor given by experiments. Okay. For this, we can still consider the spatial solutions by depending only on x. So we can construct spatial solutions and show it almost the solution is stable. Yeah. And the third one might be the heat exchange. Okay. This is called a Rayleigh flow in physics. Yeah. In this case, there is a given source term in the conservation of energy. Okay. So we can also construct the spatial solutions depending only on x and their transonic shocks. Okay. Here, this is some reviews. Okay. And now we return to the simplest piecewise uniform normal shock case to introduce the main ideas used in these studies of transonic shocks. Okay. The main ideas are similar. Okay. Okay. We first list the typical difficulties in the studies of transonic shocks for the Euler equations. Okay. The most difficult one is not the free boundary, but the Euler system for steady subsonic flow. It is elliptic and hyperbolic composite. I will explain later the definition. Okay. And the method to deal with this is introduced by Professor Shu Xingchen. Okay. The first one is using the Lagrange transform, and the second is the characteristic decomposition. Okay. So up to now, we have a quite good theory for 2D because of these two methods. Okay. For 3D, we have very few results because the 3D steady subsonic Euler is also elliptic hyperbolic composite, but we don't have a good idea to decompose it. So that's why the 3D is more complicated, and few results you know now. Okay. So the second difficulty might be the free boundary, okay, namely the shock front. Okay. And recall our definition of transonic shock solution. Okay. Here we assume the supersonic flow is smooth C1, and the subsonic flow is also C1, which means that to solve the supersonic flow, we can use linear relation and then nonlinear iteration. Okay. For the subsonic flow, we can also linearize, study the linear problem, and then get the solution of the nonlinear problem by iteration. But the shock front is the nonlinear structure of this problem. It cannot be linearized. Okay. So to deal with this, the idea is to decomposition of the Rankine-Hugo conditions, and then establish a suitable nonlinear mapping, and then show a fixed boundary exists by the Banach fixed point theorem. We can use this because we are dealing with a small perturbation problem. We have a special solution. Okay. So the third one is a nonlinearity. Okay. For the subsonic flow, we first linearize it, and then get the solution of the nonlinear problem by the fixed point theorem. Okay. So this is the main difficulties, and later we will give ideas how to deal with. Okay. The first one is the Lagrange coordinates. Okay. Here, xy is the original physical coordinates xy, but now we introduce cosine equals x, but eta is a function of xy. It is given by this integral expression. Okay. Eta xy measures the mass flux between the lower wall and the streamline passing the point xy. Okay. Here, the streamline. Okay. Remember we have a velocity field uv. A streamline is an integral curve of this vector field. Okay. So a streamline is an integral curve of this vector field. Okay. So eta in some sense is the mass flux between two streamlines. Okay. And eta is well defined. Okay, it does not depending on the curve. Okay, on the curve joining the points and joining the point of x, 0, 0, and xy, because we have the conservation of mass. Okay. So in 2D, we can introduce Lagrange coordinates, okay, but in 3D, not possible. Okay. Now we can write the Euler system in the Lagrange coordinates. Okay. We can write it in the conservation form. Okay. And the first is the conservation of mass, and these two are conservation of momentum. And the last one is the Bernoulli law. Okay. Minjing had introduced it. Okay, the same one. Okay, the same one. Okay, so the function E0 is given by the supersonic data here. Is given by the so it is given.
Psi?
Sorry.
You defined eta, but what is psi?
Gamma. Oh, okay. Gamma is okay.
X.
X.
Original X.
Oh, okay. Cosine, right? Okay. 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 Yeah. Yeah. Okay. So this one is actually the conservation of energy. They are equivalent. Okay. Later we will use this to deduce the Rankine-Nicoll conditions. Okay. To deal with the free boundary, we need the Rankine-Nicoll conditions, and we derive it from this. Okay. The other form is a symmetric form. We can write it in this with A and B are both symmetric matrices. Okay. They are symmetric, and here U is the unknown UVP. Okay. If U, V, and P is given, we can solve the density from this because E equals, okay, recall the definition of C square, it is P over rho. Okay, so if we know U, V, and P, we can solve rho from the Bernoulli law. Okay. Okay, this is a symmetric form. Now we introduce the definition of elliptic and hyperbolic composite system. Okay. The first one is we require that A is non-singular. Okay, we have a system, and we require A is non-singular. The second thing is that we need that the inverse of A and the product B. Okay, their product is diagonalizable on the field of complex numbers. Okay, we require this matrix. This product is diagonalizable on C. Okay, now if all of the eigenvalues are real, then we call this a hyperbolic system. Okay. For supersonic flow, it is hyperbolic. We can check it. Okay. The other is that if all of the eigenvalues are imaginary, not real, then it is called an elliptic system. Okay. The third case is that some eigenvalues are real, but the others are imaginary. In this case, it's called a hyperbolic elliptic composite system. Okay. The real eigenvalues represent some hyperbolic effects, and the imaginary eigenvalues represent some elliptic parts. Okay. This is a definition of the elliptic hyperbolic composite system. Okay. Up to now, there is no general theory of such systems. Okay. For the purely elliptic and purely hyperbolic, we have a good theory, but for this case, there's no theory. Okay. Yeah. The other idea is characteristic decomposition. Okay. It is quite simple. Now we assume lambda is an eigenvalue. Okay. Lambda is an eigenvalue, and L is a left eigenvector. Okay. Now we multiply L from left to the partial differential equations, and we get this. And because L is an vector, okay, so there holds L lambda A equals LB, okay, just from the. So substitute into this, we get this one. Okay. So here LA is a vector. Here is also vector, so it is a scalar. It is a scalar equation. Okay. This is called the characteristic decomposition. Okay. Now the steady subsonic Euler system is the elliptic hyperbolic composite. Okay. Now by the definition, we can find that there is one real eigenvalue, okay, lambda 0 equals 0. Okay. And a pair of complex eigenvalues, okay, lambda plus and lambda minus given by this, and here lambda r and lambda the imaginary part. Okay, here m is a Mach number, because we assume here the subsonic flow it is less than 1. Okay, so the static subsonic Euler is a hyperbolic elliptic composite. Okay, this is the most difficult part of such problems. Okay, but fortunately in 2D case we have now we can decompose it into the elliptic part and the hyperbolic part. Okay, now how to get this? Because remember we get not just here, okay. Just here, we have now lambda be the imaginary eigenvalues, okay, and L be the associated left eigenvector. Okay, we just doing this, okay, just do direct computations. Then we just get this. It is a first order elliptic system, okay, because here L is equals real part and imaginary part. Lambda has real and imaginary parts. Okay, substitute in it and then separate the imaginary part and the real part. We get these two equations. And here W is V over U. So it is a elliptic system of pressure and W. Okay, P and W. Okay, here is the coefficients. Okay, these are coefficients. Okay. We can check it is a elliptic system. Okay. Okay. Yeah, this is the hyperbolic part. It corresponds to the lambda 0 equals 0. Okay. The first one is Bernoulli law. We have already known that, and this is the invariance of entropy along streamlines. Okay, Minji also introduced that. Okay, so we can get that the hyperbolic part is one algebraic equation, and this seems to be ODE, but actually there are two algebraic equations. So for this case, the hyperbolic part is quite simple. Okay. So in detail, we mainly deal with the elliptical problem. Okay. And now we have dealt with the Euler equations. So the second thing is a free boundary. Okay. So how to deal with that? Okay. Now from the conservation form of the Euler equations, okay, that's from here, and by the definition of Rankine conditions, we can write down all of the H conditions like this. Okay. Here we assume the shock front in the Lagrange coordinates is given by this function psi. Okay, it is also C1, and then this is the H conditions. And the last one means that the Bernoulli law holds even across the shock front. Okay, even there's a discontinuity, the Bernoulli law still holds. Okay, it is invariant and streamline even past the shock front. Okay, this is the first one. Now, by the third one, we can solve psi prime. Okay, we can solve the derivative of psi. Why we choose this equation? Because by the physical entropy condition, the denominator is non-zero. So we choose that to solve psi prime. Now we substitute psi prime into these two H conditions. We then get.
So may I have a question? For example, if you choose the second one to choose
this one,
to decide the free boundary,
there would be a problem because if we get this, okay, minus U C loss and V over U, right? And for the background solution, it is 0. Yeah, so it is not good. But this one is good because by the physical entropy condition, the pressure should increase by crossing a shock front. Yeah, so it is non-zero. Okay. Now we substitute psi prime into the first two H conditions. We get these nonlinear boundary conditions, okay, on the shock front. So now on the shock front, we get G1 U, okay, G2 U. Okay, we have these two conditions, and the third one. Okay, the third one is this one. Okay, is this one. So we have three conditions and get these three G1, G2, and that. Okay. This is a decomposition. Okay. And I would like to say this is an assumption. Okay. We assume psi 0 equals 0 because for such transonic shocks, we cannot determine its position. Yeah, we have to assume that it passes as a fixed point. Okay. We cannot determine the position from the mathematical mechanism. We need this assumption. Okay. Now we can formulate a free boundary problem in the Lagrange coordinates. Okay, recall we assume that the supersonic flow is always given. See, it is known. So we just have a free boundary problem. The shock front is a free boundary. It is passing a fixed point, and here is a supersonic flow. Okay, and this domain given by omega psi. Okay, and the shock front. Okay, its equation is psi equals psi eta. Okay, so this is omega psi, and on the upper and the lower wall, we still have the slip condition. Okay, W equals 0 because W is V over U. V0 means W0. Okay, so W0, and at the exit, recall we have the back pressure. Okay, we given pressure at the exit, so we still have the pressure. Okay, P is given. Okay, it is given, and on the shock front we have these two and this condition. Okay, these are the conditions on the shock front. Okay. And recall, we have reduced the Euler system to this form. Okay, Euler see that they are equivalent to the original Euler system. They are equivalent, provided that U and 0, U is not equal to the sonic speed, and the Mach number is not 1. If this holds, then this is equivalent to the original Euler equations. Okay. Yeah. And that's the elliptic part, and these two are the hyperbolic part. So now we have formulated a free boundary problem. Okay, so how to deal with that? Okay, the strategy is as follows. Okay, now we first define a set as a sigma. Okay, as a sigma. Here is some which the Holder space. We don't care that. We just give a set as a sigma, and then we choose any function psi from a sigma. Then we know we have this domain. For psi is given, we have a domain. The domain is fixed. Okay. And on this domain, we consider the boundary problem. Here, the Euler equations, okay? That means these are 4 equations. And on the upper and lower wall, the stable condition. And at the exit, given pressure. And on the shock front, now we have 2 conditions, G1 and G2 equals 0. Okay, so this is a fixed boundary problem. Okay. Now, because we call this as problem okay, star. Okay. Now, assume we have a solution, have a unique solution to this problem. Okay. Okay. Now, if we have a unique solution, U, okay, have a solution. Now we solve this. Okay. This is actually very simple. It's just right here. Okay. Okay. So these are actually set here eta equals that equation from 0 to eta, and V minus okay, the supersonic flow it gives, and the P supersonic flow at the point it is psi s yes. Okay, just given by this. See, the supersonic flow is given. The psi we have fixed it, and this we have solved. Okay, so this is already known, and we just integrate get the new function theta psi. Okay, and we can show that theta psi still lies inside, okay, because it is a small perturbation problem. It is still lies inside set. So by this way, we construct a nonlinear map from the psi to the theta psi. Okay, so it is a nonlinear map. Now we assume that if psi star is a fixed point of the map N. Okay, so if psi star is a fixed point, okay, a fixed point. And from this psi star, okay, we then solve this problem with psi replaced by psi star. Okay, we solve this problem with psi replaced by the fixed point. Then we get a solution. This solution we denote as a U star. Okay, then the supersonic flow and the U star and the psi star is a transonic shock solution, because by this, okay, from here get this, because by this, okay, on this boundary psi star, this holds, and because it's a fixed point, this also holds. So all of the conditions holds on the free boundary. Okay, it is a free boundary. So this is a main strategy. So now the main part is to solve the nonlinear fixed boundary problem. Okay, this is easier because we have a small perturbation problem, and the elliptic part is algebra equations. There are no loss of derivatives, so it is quite standard. And then we linearize this problem, and then using the nonlinear iteration to get a solution of this nonlinear fixed boundary problem. So we just skip to the linear problem. Okay. So here is the elliptic part, okay. And this is a Cauchy-Riemann system of the pressure and the W, pressure and W. And F1, F2 are non-homogeneous terms. And the boundary conditions are like this. Here, the pressure, W, and here, the pressure. This comes from, because we consider linear problem. From G1 and G2 equals 0, we linearize it, we could get this. The linearized version is the pressure equals H1 U, and the other is the velocity, U, H. So from this we can get a boundary condition of the pressure and the velocity U. So this is from G1 and G2. Now for the elliptic part, we use only this. We use this one to here. So we get this Riemann Hilbert problem of Cauchy-Riemann system. The point is that for this problem to be solvable, there should be compatibility conditions between the non-homogeneous terms, which means that F1, F2, and G and H1 should satisfy some integral conditions. Actually, from this we can derive a Neumann problem, a Poisson equation. So actually, obviously, it needs a solvability condition. So this is a mathematical reason that why such special transonic shocks are not stable, because for it to be solvable, we need such a condition. So this is a mathematical reason why it is not stable. Maybe I'll take it. Once the elliptic part is solvable, once we solve this, now we solve the hyperbolic part. Remember, recall now we have got the. Recall from the elliptic part, we have got the pressure and the velocity. The W, the V over U. We have got this in the domain. By solve this. And now this is so especially we know their value on the boundary. Especially we know this. And now, and we also recall that we have this. We know the U on the boundary. So from these three under the Bernoulli law, we call the Bernoulli law. This is known. And now on the boundary, we know the pressure and U and W. These are given. So we can solve rho. We can solve the density. So we can solve the density, and we also know the pressure. So by the state function, we recall that P equals. Now we know pressure and the density, so we can solve the entropy. So we get the entropy. So we get the entropy here. Now we have recall that the other elliptic part is this. S equals 0. We have this equation. So from this boundary data and this equation, so from this we can get the entropy in the whole domain. So we also get S in the domain. And from this, we still use this state function. We know the pressure and the entropy in the whole domain, and we get the density. So we get the density. And now, again, by the Bernoulli law, we know the pressure, the density, and W, because it is solved. It is already solved. So we can get the velocity U in the domain. And W is known, U is known, so we get a V. So from this, we solved the pressure and the entropy and the U and the V. So the whole linear problem can be solved. By solving this linear problem, then by some nonlinear iteration, we get the solution of the nonlinear fixed boundary problem. And then, as we showed before, we can get the solution of the free boundary problem. Okay, I still have some time. Okay. 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 So I just okay. There's one problem I mentioned before. If the supersonic flow is not smooth, how to deal with this? Okay. The difficult part is that okay, if the supersonic flow is not smooth, we cannot linearize it. Okay, this is quite difficult. Okay, so we have to use okay, if the supersonic flow is not smooth, okay, we have to solve a weak solution of a conservation law, hyperbolic conservation law. But now there are two boundaries, and what's worse is that if we use front tracking, then there are wave reflections. Okay, but unfortunately for the straight arch, the reflection coefficient is 1, which means the wave will not become weaker. It may be the same, or maybe become stronger. So it is seems to be impossible to construct a weak solution in the duct by the front tracking method, because the reflection coefficient for the background solution is 1. Okay, so this is the first part. This problem is still unsolved. Okay, for the weak solution of supersonic of hyperbolic conservation law with two boundaries, and the reflection coefficient is 1. I don't think that's the result. Okay. The other part is that even we get the supersonic flow, but here this shock front cannot be smooth. Okay, because now we take a look at the, for example, subprime, okay, the RH conditions, okay, V minus the psi, okay, here the supersonic flow. In general, supersonic flow for a given spatial curve, it is only BV. It is only a BV function. Okay, so this means that the psi is only Lipschitz continuous. Okay, so the free boundary is Lipschitz continuous. So we know that up to now, if the boundary is Lipschitz continuous, there's no C1 alpha estimate. No C1 estimate of equations. Okay. It depends on the gradient. Okay. If for quasi-linear equation, elliptic equation, if the coefficients depends on the gradient of the solution, there's no such result. Okay. So how to deal with this? So the first part is existence of hyperbolic, the supersonic flow, and if it exists, how to deal with this free boundary? It is not smooth anymore. Okay. So this is, I think, also an open problem, maybe. Yeah. Okay. Anyway, I don't know how to deal with this now. Okay. But I think it is really interesting because the physical picture shows that the supersonic flow is not smooth. Okay. And one more consideration is that the subsonic flow may no longer be smooth anymore. For example, we have studied the Maher configuration. Okay. 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 For Maher configuration, there are 3 shocks. Okay. There are 3 shocks and a contact discontinuity. Here the flow is subsonic, here supersonic, and here supersonic. Okay. Here supersonic. And for this case, the supersonic flow is not smooth. And it turns out that the supersonic flow is also not smooth. There is a contact discontinuity. So maybe in this case, the supersonic flow is also not smooth. But how is the structure? What's the structure? Okay, we don't know. Okay, so that's my problem. Okay, yeah. See, so I think I stop at this point. Okay. Okay, and the last one. Okay. Thank you. Okay. Yeah. Okay. Yeah. Thank you for coming here. Yeah.
Any question?
Yeah. Okay.
I have several questions. So first, in the earlier part of your talk, you had some result on the unique, global uniqueness.
Oh, yeah.
Could you?
Okay. Okay. Remember, we have a spatial solution. Okay. Yeah. Okay. we have a special solution, okay, the straight duct and the straight shock front and the uniform supersonic flow, okay. Supersonic flow is a constant, okay. And here V equals 0, and here the measure on pressure, okay. Our global uniqueness shows that if is a constant, okay, the constant supersonic data, and if this problem, there is a solution. This solution must be the special solution. Yeah. So we assume that the solution supersonic, subsonic, and shock front. And in this class of solutions, if there is a solution, this solution must be the special solution.
In which class?
In the class of okay, here supersonic, here subsonic, and for subsonic we require it to be C1. Yeah.
For physical.
Here is the pressure. Okay. Yeah. Okay, this is a global uniqueness. Okay. From this we can show that if for here U B minus, if P is not the one determined by the supersonic flow, then there is no solution. There is no such solution. Yeah.
Okay, so my second question is earlier when you talk about the stabilizing effects, you also consider friction and also other
Yeah.
flow, fan of flow. So there, if you consider such result, then do you have some kind of stability?
Yeah. For the frictions, we have submitted. We have the stability. Okay, it can be
So
shown.
basically, if you consider this effect, probably that will change somehow the behavior of one-dimensional solution.
Yeah, of course, because there's a lower term.
Which means that somehow maybe
The
flow
one-
would
yeah,
accelerate or decelerate.
Yeah, for this case, the subsonic flow will always increase to sonic, and the supersonic will decrease to sonic. Yeah, so this special solution is a variable, not constant. That's the reason why it is
So
stable.
is there any particular reason why you consider friction in particular?
Because friction, you can see books on the gas dynamics. Okay, this is one of the effects they considered for flows in ducts. So it has a name, fan flow. Yeah.
So this case you have uniqueness.
No. No, for this case,
For this case, the other case.
just for
with
yeah, for the,
friction, with friction.
no, for friction,
What kind of result is this?
instability or uniqueness.
Yeah. What?
For stability,
Yeah.
Oh,
You got
so-
stability.
yeah, for stability, yeah, we have got for almost the background solution stable.
The shock location can unique.
Yeah,
Because friction, right?
Yeah, for this case, just like the geometry effect.
Yeah, this is what
Can be
I mean.
This
uniquely.
effect gives you some kind of monotonicity effect.
Yeah. They are similar.
Like the geometry.
Yeah, similar.
Divergent.
Yeah, similar. Yeah. Okay. But also this is a very simple model because physically, there's for the hypersonic it might not be U square, maybe U4 or U6. It depends on the Mach number. Yeah, so actually, for the physical situation, it is quite, the damping term. Okay, it might not be a power. This might be quite.
Not a square.
Yeah, maybe you. Yeah, and this Darcy friction. Okay, like sigma may also depend on density or something like that. That's a physical the experiments have showed.
So
But
here, the parameter mu is positive.
Yeah. For our case, we assume it is a constant. Yeah, for simplicity, but actually, it depends on the density, and this might not be square. Okay.
You already have a density there.
Density
You
mu rho u square. Rho comes because the definition of the Darcy friction factor. It is the stress force x on per mass of the gas. It's by the definition. Okay, so here the rho.
And the previous three throws an instability. Is it the linear spectral instability?
For the simplest background solution, straight line and constant, not stable. Not stable because we show actually that for the linear problem, there requires a solvability condition. So if you give pressure this way, generally you cannot satisfy the integral condition. So there may not solution. Yeah. Yeah.
And also you mentioned about the front tracking method cannot work for deflection.
Yeah. Because for straight ducts, the reflection coefficient is equal to 1.
So you mean the norm is 1?
The reflection coefficient, it can be calculated by the Riemann problems. Yeah, which means that the wave will not become weaker. Yeah, so.
But still you can track.
Sorry?
I'm not expert, but still you can track it.
Can contract?
Yeah.
Front checking, yeah.
Front-
You construct the approximate solution. You can
Front tracking is up to now.
construct the total variation cannot.
Yeah. Yeah.
Yeah, you're right. You can construct how to estimate.
Yeah. So because the reflection is a 1, maybe sometimes larger than 1, so we cannot construct the limit functional to control the total variation. Yeah.
There is initial boundary wave problem for hyperbolic equation. You know very well, but if you reflect wave in out less than 1,
That's okay.
very easy to do it.
Yeah.
Just there.
Yeah, both equal to 1. So this is a problem. Yeah. For example, if this is larger than 1, it's smaller than the product is less than 1. Yeah, but not.
Not two, both.
Yeah.
More
For
difficult.
one word,
Yeah, you can do it. One called infinity half space, and you can do very well.
Yeah.
Between two other reflection waves.
Yeah.
One of them less than 1 and 5, you can control it.
Yeah.
Not both reflect close to 1, but because then it's open. Yeah. So you're interested in that. Boundary conditions. Yeah, it's strange that it could be. Should there be some ways to do it? Another thing that involve hyperbolic line, I don't know, the different from elliptic now. Free band optimal regularities, derivative, total variation of the derivative.
Free boundary, right? Yeah.
Boundary.
Yeah.
That a little better than ellipses, but it never reached to say 1.
Yeah.
So do you have such examples?
Oh yeah, this is because shock waves is not bad, optimal regularity a little better than ellipses. But never you reach to say 1. You can compute total variation of the slope. The total variation could be bounded. But that optimal you cannot better than that. So different, you limit it from the ellipses, you get C1R, C1 alpha, then C2 alpha, C infinity, you can get regularity. Free bounded problem for elliptic. But here optimal, that you cannot better than that.
And also you're saying some discontinuity subsonic.
Yeah, maybe. That's just my observation from the Macher structure. So I don't know.
Oh, this is because coupled under the two linear equations.
So yeah.
You have elliptic coupled to transport equation.
Yeah.
So can you observe it and be able to of such jumps?
Here.
Explain more intuitively.
Oh yeah.
Yeah,
It's
here.
physically converted sheets.
Yeah.
You can observe.
The jumps of maybe density, entropy. Yeah.
The same compressive
Yeah,
rotation.
yeah,
yeah.
Incompressible,
Yeah.
They exist physically.
Yeah.
But this physics, everything physics.
Yeah.
They know how to do it, the same couple.
Yeah.
That's the problem, The problem is optimal regularity cannot move up. You have to stay this kind of space.
Yeah.
Maybe space is very delicate.
Yeah. Maybe there are some gap. Maybe there are much better space to describe it, but yeah, don't know now.
Question,
Since it's an introduction,
Yeah. No, this is informal.
Yes.
Yeah.
So if you ask
And a
questions,
stupid question. You have two types of irregularities, right? One was the shock,
Yeah.
and the one was, I think, like vortices.
Okay.
So from the experiments, physical experiments, which one is arising like first?
Okay.
For the question,
Yeah. For the unstudied case, it is too difficult.
well,
Or in the theory, what
the
you
theory-
expect to get first.
a little depend initial data, I would say.
Yeah.
Most cases will first shock first.
Oh, really?
Yeah.
So
Yeah.
shock, then
If initially very nice, shock
Yeah.
first. Isn't the compressibility, the flow like the speed depends. Behind the fast, this slow down, then very easy complex. Then you have a body characteristic is fast, like this speed fast. Behind the wave and slow, then it forms singularity, shock wave. Now vortex should put the generate by two shock interaction, you can generate additional vortex. You start no vortex, there is a certain
you expect like vortex to be aftershock usually.
if initially nice.
Yeah.
Yes.
After initially this kind of vortex data, then initially very nice,
Initially.
very smooth. Then you later time,
Yes.
shock more, So the both the Chris Dolo, he looked at now about special relativity, all IP similar special relativity. He proved that both
Okay.
1,000
stickable. Yeah, yeah.
1,000 pages, very
Yeah.
simple. He just proves formulation of singularity.
Yeah.
His is the theorem of shock first. For those kind of perturbation in that class.
For this case, the proof will be 2,000.
Well, that could be simple, shorting. I think climate they are writing and they short 300 pages.
Proven.
Yeah.
Thank you.
Okay. Thank you. Okay. Maybe we stop here. Okay.
Yeah.
Okay. Thank you.
Thank you.